Bueno, después de esta pausa, quiero invitar a Gilberto a que dé la segunda charla. Esta charla va a ser sobre Feature Engineering y Feature Selection. Esta es más técnica que la anterior y espero que os guste tanto como la anterior. Muchas gracias. Thank you.
Okay, let's start. Kaggle tips for feature engineering and selection, right? Well, Kaggle is all about accuracy, right? The metric for the competitions are different, but the winner is the one that provides the best solution in terms of minimizing the error, right? Doesn't matter the metric, but the idea is minimize as much as possible the error. So what we need to take into account when we want to achieve high accuracy single model, right? The quality of the data set and the ground truth. We must avoid noise in the features and the target labels. It can influence the accuracy of the final solution. The size of the data set, of course, if the data set is too small, probably the accuracy is not going to be so good. Feature preprocessing, especially for linear models, choosing different preprocessing for each feature can lead to different final performance. Feature engineering, as I told on the previous talk, feature engineering I consider very important. And we need to use a lot of human intuition when building features, on engineering features, right? Feature selection, model selection, and hyperparameter optimization also are present in Kaggle. And if you want a single model with high accuracy, you need to care about all these topics here. When it's talking about multi-model, like building multiple different models, then other things also take into account in terms of accuracy. Of course, the accuracy of single models, we must take into account. If you have very good single models, probably mixing or ensembling the multiple models will lead to even better accuracy. Diversity of the models. What I mean diversity? In many ways. Diversity means using different training algorithms to train each model. For example, mixing a decision tree-based algorithm with a neural network algorithm usually tends to be very good. Model selection. Sometimes when building models for Kaggle, we tend to build several models, and we try to do some kind of model selection to mix that model or to combine all those two models. And sometimes combining one model decreases the overall accuracy of the local validation metric. So model selection is very important, and doing it in the proper way also is very important to model accuracy. And sometimes some post-processings are also important in terms of accuracy. Okay. But one initial step, and very important for Kaggle, also in the real-life problems, is exploratory data analysis, right? Is when you pick the data set, load it, and start to analyze the variables and get used with the variables, right? You can use any tool to do that. You can use R, Python, MATLAB, even an Excel spreadsheet. Any tool available you can use to do that kind of analysis. And it is very important in terms of getting used with the features in order to prepare the model for a machine learning model, machine learning training algorithm, right? But also, getting that feeling about the variables is good for feature engineering. And feature engineering in terms of high accuracy models, it's a little bit of an art, right? It's some kind of skill you can develop, but some people do it better than other people, right? So, and that's why it's hard for a machine to mimic that kind of feature engineering in, for example, AutoML that was talking before. So I pick one example of Kaggle, the Santander Value Prediction Challenge. It was 1 year ago. The train set, it's almost a matrix, almost a square matrix, almost 5K rows by 5K columns, right? And it was presented or shown us to Kagglers as a black box. We have no idea what are the features, but we have just a binary target. We have just the target variable available. It's not a binary, it's a regression model. But we have the target, and all other features are anonymized. And this is a look of the first columns of that matrix. Of course, there are 5,000 columns of that matrix, but just taking a look at that matrix, you can see that the values are extremely sparse on that matrix, right? And we can see the values on the target, the second column, the target variable, are pretty big in terms of value, right? And performing some EDA on this data set, I found that the values present on the target label, for any reason, were also present on the other 5,000 columns, 5,000 features of this data set, right? The exact value. For example, the value on the first row there, 380000, was also present on the features. And it was an insight. So based on that, I created a hypothesis of, well, maybe this is a time series problem they tried to hide from the data scientists, right? And eventually, I found my hypothesis to be true, because what I made, I created a lot of algorithms to unshuffle the columns and the rows like a Sudoku game in order to find this. Just unshuffling the columns and the rows at the same time is a 2D problem. I found the target variable are present on the other features, but in different rows of the data set. And if you take a look, you can see it's exactly what my hypothesis is. It's a time series problem. And there are a lot of values that just repeats on this data set. And that property makes us able to just to get the target label perfectly for the test set in Kaggle. But in this competition, it affected around 50% of the rows only in the test set. So the other 50%, we had to build machine learning models also to predict the target label, right? But this kind of property, I was only be able to detect doing exploratory data analysis, and of course, I made my hypothesis, a lot of hypotheses about this data set, and happily I found one that true. Okay, but taking that other Kaggle data set, Titanic data set, it's also possible to have an insight about the features, just calculate the correlation of the numerical features and the target dependent variable, right? For example, the Titanic data set is based on the Titanic disasters, and we have to classify if the passenger survived or not, just based on some few features like P class, passenger class in the Titanic, age of the passenger, siblings, and fare of the ticket fare of the ship. And there are a few other variables also, but they are pretty simple. It's a small, of course, a small data set, around 1,000 rows. But just calculating the correlation of the target and some variables, we can see the survived column. We see a very high correlation with passenger class and fare of the ticket, right? So just looking at that results, it's very likely that the passenger class influenced if you survived or not to the Titanic disaster. My first hypothesis was probably they saved the first class first, then the other class. And it's exactly what happened. But at the same time, the fare also is showing that because there are 0.25 correlation of fair and the survival rate, right? And usually the first class are more expensive than the other class. And what I'm trying to say is a simple correlation calculations is enough to start to get some feelings about the data, right? I plotted this matrix in this form in numbers, but there are other ways to plot that kind of correlation matrix as a matrix of colors, whatever. It's just to show you that EDA is important. And feature engineering. Okay, feature engineering, as I said, in my opinion, is a kind of art or skill you must develop. But according to the wiki, is the process of using domain knowledge of the data to create features that make machine learning algorithms work. Feature engineering is a fundamental to the application of machine learning and is both difficult and expensive, right? This is according to wiki. And Andrew Ng, just the beginning, he said, coming up with features is difficult. So that's what I said. It's really difficult for humans to do feature engineering. It's more easy to do brute force feature engineering, but we don't have all the time of the world to do that. So that's why it's a little bit of an art, right? If you use the human insights to build feature, usually we build better features for the model. And starting with feature engineering for Kaggle, we can use any kind of combination between numerical features. Any kind of combinations you can think about, right? That's why I said there's infinite way to do feature engineering. You can combine all the features in the data set with all the other features in the data set in many forms as possible. You can combine 2 features together, 3 features, 4 features. You can do any kind of combination. You can provide a weighted average. You can do some log combinations, rank-based combinations, calculate some math functions before the combination, whatever. The fact is, there's a lot of ways to do feature engineering with numerical features. Okay, inputting NaN. This is something very basic, but sometimes people do it the wrong way. What I used to do in Kaggle, especially in Kaggle, people doing the wrong way, is suppose you have these 2 features, and there's some non-available values for some rows. How we can input that non-available values? First of all, we need to input the non-available values for algorithms, especially linear algorithms or neural network algorithms. So it's a must. For decision tree algorithms, it's not necessary to input non-available values, but for linear, we must input. So we always have to have a strategy how to input that. And the first thing comes to the mind of people is just input with the mean average of that features, right? But it's not necessarily the case. What I do in Kaggle is when inputting the non-available variables, I create 1 extra column just to tell the model that this position, this specific feature, and this specific row was inputted. A binary flag telling that. So in this case, I just added 2 new columns and telling exactly the position where the feature was inputted, right? And after that, I scale the numeric variables, and the features that have no value before, I input with 0, right? That's the way. If you're running a linear model and the value is 0, it means there's no importance. Doesn't matter which value at times with that, it will always be 0, the result, right? This is just a way to tell the model, okay, these features have no importance, but I added the binary flag telling the model that feature was inputted, and maybe there's some value to learn from that missing features, right? This is a good way that works good in Kaggle. I tested a couple of times in real life, it always works, but this is a way I like it because we don't lose information doing that. Categorical features, there are many ways to treat the categorical features. We can just use a single label encoder, just replace each category by a number. We can use the categorical features to group and calculate statistics of other numerical features. We can use frequency encoding directly on the categorical features, just count how many times each category appears on a variable. We can process using one-hot encoding, like creating a binary matrix where each column is representing the categorical feature, right? But usually there are some issues transforming the categorical using that strategy. For example, if there's a high cardinality categorical feature with 1 million different values, we need to build a matrix with 1 million columns. And some algorithms needs to input a dense matrix. And we are talking about a large amount of run just to build that kind of matrix. Another way to decrease the amount of run necessary to transform the categorical features is the trick of using the hash encoder and then do the one-hot encoding, turning the binary matrix. A hash value, you can use the modulus of a hashing value to limit the size of the categorical values, right? There's a drawback on this strategy that we can have hits of different categories with the same value, but in general, if there's a pretty high cardinality, it usually works well. And we avoid that problem of having huge number of columns on the matrix. And the last one that I like better, and I use a lot on Kaggle, is the mean target encoder. The mean target encoder is when we replace the category by the average of the target label for each category. And that's what I'm talking right now. So the idea of the encode the targets in the categorical variable is to use the information from the dependent variable, but keep the size of the categorical variable. Using only one column, one feature on your training matrix, right? Keeping the same size of the categorical variable. This kind of technique works both in regression or classification tasks, but usually it works better if the category have a lot of values. It's a high cardinality category variable. But once you are using the target value to encode each category, we need to process it using a cross-validation approach to avoid leakage between the folds, right? One example of how to do that is that simple table when we have color and target value. So the idea is, for example, for the color red, we have the target 0, 0, 1. So what I do, we just take the average, and every time a red appears in that variable, we replace by 0.33, right? The same for blue. We calculate the average of 0, 1, 1, and every time the blue appears, we replace by 0.67. The same for green. That's the idea. It's pretty simple. They're not new here, but we can keep the size of the feature, and that kind of value on the variable is easier for a machine learning to learn the problem and to solve the problem they are attacking. Okay, this is another Kaggle example, Amazon Employee Access Challenge. That competition is well known to have, because it have only categorical features, high cardinality categorical features on the data set. So that competition is perfect to use target encoding. And the first column is the category, the variable name, right? There are I plotted 6 category names of variables. And the second column, I use a direct way, exactly as in the previous slide. I just calculate the average, the target, and I used that value to replace each category for each feature. This is the leak way to do that because we leak the target value when we do that. And that's why the AUC for that features are pretty high. If we compare with the last column using the 5-fold validation strategy to build the target encoding. But of course, the last column is the one that is valid, the one that we can use to train a machine learning model. And what is the advantage of using a target encoding? Because when we do that kind of encoding, we can automatically or directly calculate the performance of individual categorical feature against the target, right? Because just looking at the categorical feature, you have no idea if that feature have a small or a big performance in terms of the metric chosen, right? Just looking at the values of the target feature. But if we do that kind of strategy, we can see single feature performance against the target. Just looking at the metric, just calculating directly the metric of the feature and the target, right? This is advantage when you're doing some kind of EDA and you get familiar with the data because we have an idea which features are more important or which features are getting the best results in terms of the metric of the competition. Okay, another advantage of the target encoding, you can combine multiple category variables. In this example, I'm combining 3 categories in a new one called 3-way, right? So I'm doing a 3-way combination. So I plotted the data frame there, and you can see this is simply the combination of the numbers of the previous categories, right? So that 3-way new category, it's possible to also calculate, transform using target encoding technique, using the cross-validation approach, and calculate the metric of this new feature that I just created. And you can see, combining that 3 features, we got an AUC of 0.82 that is higher than any other AUC we see before. And it's logical since we are combining multiple features, right? But the idea is, without doing the target encoding transformation, there's no way for us to know the power of each feature before doing that, right? There's one trick in Kaggle, usually works pretty well, but it's pretty easy to overfit if you do it the wrong way. I mean, if you don't process it in a cross-validation strategy. This is a single Python code, how I use to calculate that. It's 2 lines of code. I just calculate the average of the categorical, of the target by categorical column, right? And then I apply the results using the merge function to a validation or a test set. That's pretty straightforward. Calculate the mean average, then apply to the test set. That's it. I already told before, the right way to do that is split your train set in any folds. Usually I use 5 folds in Kaggle. It's proven to be a good number to start working. Then, for each one of the folds, of these 5 folds, we split in a valid test set. And the other 4 folds you use to calculate the metric, right? The metric of the target for each category. And we apply the results to the validation and to test set. That is pretty simple, using that function on the previous slide. But to avoid leakage, you need to calculate the same values for the train set. And to calculate the same values to the train set, we need to run an inner nested fold or an inner cross-validation only on the train set. Remember, we split the validation set, we remove the validation set, use all the train set to calculate the metrics of the target and apply to the validation set. But now we need to do exactly the same only in the training set. So we run a nested fold strategy for validation again on the train set. And you use, for example, folds 1, 2, 3 to calculate the metrics, and we apply the results to fold 4. So we repeat it 4 times, and we got a target encoded training set and a target encoded test set for one feature, right? Doing that is very hard to overfit the training set, doing that correctly, right? But if you made any mistake in this process, probably you get a model extremely overfitted. You get a model with accuracy close to 1, you get pretty happy, then when you submit it to Kaggle, you get the worst result as possible. Aggregations is another way to build features that is very good in terms of feature engineering. What I mean about aggregations, I mean aggregate one numerical feature based on a categorical feature, right? Again, using the Titanic data set, what I'm doing is, in this group by function, I'm aggregating the age numerical feature by each one of passenger class. So I'm aggregating age by passenger class. In a way that I'm calculating the count, the frequency, the mean average, the maximum age, the minimum age, the standard deviation, skewness of age for each passenger class, right? And the table on the bottom shows the results of this aggregation, right? And it's just a matter of call the merge function to aggregate that statistics back to the original data set. That way, right? Call the merge function on the passenger class variable, and automatically that aggregations are merged with your training set. Every time a passenger class, for example, 1 appears, it will replace the variables on that row by the ones we got from the aggregations of the previous slide. This is one kind of feature engineering that can be easily automated because it's just a combination of categorical and numerical feature. But usually it makes easier the life of the model to learn that problem or to solve that problem, to decrease the maximum as possible the error metric. Okay, I already talked about scaling. That is not necessary for any decision tree-based model, but it makes difference in linear models and neural network. That's why for Kaggle, people ask how to scale the data set correctly. And I said, there's no way to scale correctly. Each case is different. I suggest to try all different scaling strategy as possible, right, for linear models. Just a standard scale sometimes is the best solution, but sometimes a minimum and maximum scaler performs better. I've seen some problems that max absolute scale is better. Sometimes logarithm scaling is better. So I recommend to perform an experiment, at least one experiment, trying one different scaler and compare the metrics, the performance metrics of using all these different scalars, right? And also, for neural networks, the activation function matters also. So for neural networks, it's a combination of scaling the data set and what is the activation function I'm going to be using to input the data on the neural network, right? There's one level more of complexity when using neural networks. And that's also one of the reasons I prefer to start using decision tree algorithms when I dealing with, when I first seen a new data set, right? Because I don't need to care about scaling. Just throw the data to decision trees and in theory, you get the best results. Don't need to scale. But also, not only the features you can scale, but also the target you might need to scale sometime, right? The dependent variable. I've seen some problems that just taking the logarithm of the target to train the model, and then the prediction function just uses the inverse function, the exponential of the predictions, makes better the predictions, right? So also, I recommend to experiment different target scaling functions. This is just some examples of how you can scale the target and then perform the inverse scaling on the target. Here's some code using the logarithm, 1 plus value, right? And then the inverse transformation is the exponential of the prediction minus 1, right? So when you call the model fit function for a regression problem, you call it using the transform on the target. And when you're calling the predictive function, you call the inverse transformer on the prediction function, right? This is straightforward. If you transform the data was using one function, you need the inverse function to untransform the data, right? This competition, all state client severity, is a regression problem, and I got top 7 3 years ago, and the trick to get that top 7 was to use that different scaling on the target variable, right? I use, for example, exponential scaling, logarithm scaling, and inverse scaling on the target variable. So I built one model, at least for each one of these transformations on the target variable. Then on the prediction time, I made the inverse transform to get the original values back again, right? And all these models I blended. I assembled the predictions in order to get that rank, the top rank, that gold medal. Okay, feature for time series in Kaggle. There is one trick for time series in Kaggle that doesn't apply for real-world problems. But what is time series? Time series is when time matters, right? And usually in Kaggle, when there's a time series challenge, they provide the train set in a period and the test set in a future period of time, right? So, but the problem in Kaggle is the test set period in future is fixed, right? The data set's fixed. The data set doesn't change. And one of the features for time series, one of the most simplest features for time series is using the lag of the target value, the dependent variable. So can you see that the equation lag on time t, it's equals to the target, the dependent variable on time t minus n. And n can be any positive value from 1 to infinite, right? Any value. You just says to the model what was the previous value, the previous before the previous, and the previous and the previous and the previous. What were the previous values of the target variable, right? But as I said, in Kaggle, they fixed the train set and the test set size. But there's no target variable in the test set. They are exactly what we need to predict. Taking that into account, for example, on the timestamp 7, we can see there is no target value on the timestamp 6. So we cannot build that lag feature on the timestamp 7, right? So if we create that kind of feature for Kaggle, it's not possible to predict, or if you predict something on the test set, it will predict random values because the data is not available in the test set. So one way to avoid that kind of problem in Kaggle, especially in Kaggle, why I say in Kaggle? because the test set size, the timestamps in test set is fixed. In a real-world problem, we always have the data today, so it's easy to predict tomorrow, right? Because we always have the data today. This is not the case on the test set in Kaggle. Look at timestamp 9. We don't know the data from yesterday, right? So there's no way to create that kind of feature. So one way to avoid this in Kaggle is find a lag, a delay on the target variable that we can build the features on the test set. In this example here, very simple example, but if you use the lag of 4 time delays, we managed to build the features on the test set. Can you see that? For example, on timestamp 6 of the of the test set, we have the value 39 for the first variable, the lag 4, right? So in the test set timestamp 9, we have the value 5. That is the last available value on the training set, right? Doing this kind of approach is possible to execute a time series features for a Kaggle competition. And sometimes people don't realize that. And people just don't understand why they are getting very bad results on the Kaggle leaderboard. But this explains many things. Also, these kind of features are pretty easy to create. Just using pandas is just a call of calling one function, for example, shift. Dimension reduction is another trick for Kaggle and for feature engineering. Dimension reduction doesn't mean that you're going to decrease the dimension of your data set. It means you can decrease the dimension, but you can add this new information to the original data set also, right? In order to increase the features, to make the features more interesting for the machine learning model. So some techniques that I usually use in Kaggle competitions is PCA, LDA, SVD, TSNN, nearest neighbor. It's possible to use nearest neighbor also to decrease the dimension, and autoencoders. This plot is a TSNE algorithm using that data set MNIST, handwritten digits, that is a very known data set. And TSNE, in this case, is decreasing the dimension from around 800 to only 2 features. Why 800? Because each input of this data set is an image of a digit written by hand from 0 to 9, right? And this digit is represented by a matrix, and the size of the matrix is around 800 pixels, right? So that algorithm, TSNE, it's an unsupervised, and it uses some embedding approach to calculate the distance between different images, and this way they can just aggregate or cluster the different images in different groups, right? Doing that, for example, on this plot, it decreased from 800 features to only 2 features and make it 2-dimensional, right? It's a very, very interesting, because if you use only these 2 features to train a model, it scores pretty high in terms of accuracy. TSNE is very interesting way to do dimension reduction in general. Denoising autoencoder, it's a special kind of autoencoder. It was used in Kaggle already. This kind of autoencoder have the property to remove noise from the data. But how this autoencoder does that? Basically, the idea is you have the inputs and outputs of a neural network, and the same data you input the neural network is the same data on the output of the neural network. So we are feeding the neural network on both sides with exactly the same data. But on the middle of this neural network, there's a bottleneck layer that it decreases the dimension of the data on that layer. It's like it decreases the number of neurons on that specific layer to make the neural network, to force the neural network to compress the data in this bottleneck layer, right? Doing that, it's possible to remove some noise from the data. This is another example. On the bottom, it's the input. We have 5 input and 5 output, right? It can be used for tabular data, image, any kind of data. And in this case, for example, is a tabular data, input 5 and output 5. And the bottleneck layer is only two neurons, right? So the data enters in 5, then decreases to 3 dimension, then 2, and then expand again. Doing that kind of architecture is pretty interesting way to build, to engineer features, because we can use information from the 2 internal neurons, the 2 bottleneck layer neurons, to generate extra features for a data set, right? And what's one of the tricks to make that architecture to work is to add noise to the input, right? For each one of the 5 inputs, we add noise. Then we expect that information goes through the neural network, compress and expand, and we have exactly the same values without the noise on the output. That's how it works. That's how it used to remove the noise, right? But what is the best way to add noise to the features? There are many ways to add noise. We can just, for example, add some random values to each variable, but usually it's not good because each variable can have a different distribution, a specific distribution of each value. So if you're adding noise, we must somehow match that distributions of each feature with the noise. The noise must match that distribution. The noise cannot change the distribution of the features. So how to solve that problem? There's a very simple way to solve that, is instead of adding noise to each value of each variable, we just swap rows of the data set in order to keep exactly the same distribution of the variable, but we change the values of each row. But we don't do it for the entire row. We select a percentage of the, we don't do it for the entire column. We select a percentage of rows on that column that we're going to swapping the values. Do you know what I mean? For example, we pick 20% of the rows on that variable and swap the values. So the values are not original anymore. They represent noise. But if you calculate any kind of distribution of that variable, it's exactly the same because it didn't change anything. We just swap rows, right? And doing that kind of row swapping is good to train a denoising autoencoder. That competition, Porto Seguro Safe Drive Prediction, was won by Michael Yeher 2 years ago. And he used some denoising autoencoders to remove noise from the train set. He was the only one that had that idea on that competition to use it. And surprisingly, it worked pretty well because he had a score much higher than the second place and the other competitors on that competition. And the architecture he used is pretty similar to the one I explained. He used an autoencoder with the bottleneck layer, and he added noise using swapping of the rows on the input of the neural network, right? Okay. Clustering is another way to build features, very good for Kaggle. You can use any algorithm you want, k-means, affinity propagation, dB scan, whatever. What I recommend is try more than one clustering algorithm in order to create categorical or any kind of numerical variables based on the clusters and cluster distance also. This is one trick. It's a real trick. Uh, Not many people do that, is to use the 3 leaves as features. What I mean 3 leaves? If you train a gradient boosting decision tree, we can train it by any rounds we want, right? And each round, basically the algorithm builds a decision tree for the boosting, right? And that decision tree, as you can see on the image on the bottom, have some leaves, and on the bottom, each row on the data set, you fall on a specific leaf on that decision tree. And that leaf has an index. And we can ask the model, the gradient boosting, to return that index of the leaves of each tree for us. And we can use it as a weak feature to add to our data set in order to improve the feature engineering, right? To add more information to the data set. People that I've seen using that kind of trick usually use that the results of the leaves in linear models, factorization machines, in order to achieve very high performance. Just an example, if you fit a light GBM model for 100 rounds or trees, using as a parameter number of leaves 10, then the result, when you predict the leaves, when you build the leaves of that tree, we got a matrix of any rows, the size of our data set, times 100, because we use 100 trees, right? And each column of that matrix, we have a leaf index ranging from 0 to 10, because 0 to 9, sorry, because we use number of leaves 10, right? It returns to us a categorical feature, a matrix of categorical features. They are very weak features, but there are important information on that features, especially about the feature interaction on this data set. That is the biggest advantage of gradient boosting, right? To explore the feature interactions. And this kind of feature usually is pretty good if you need to achieve very high accuracy in your models. Because high accuracy, as said in the beginning, it's a function of the diversity between the train set and the algorithms used to train the train set, right? For natural language processing, one trick I have is the classical algorithms. Try also the classical algorithms, but try the transfer learn algorithms also. I mean, using the state of the art of we have right now, the huge models built by Google and Facebook and others to extract the embedding information for each sentence and build the more features for your data set. But also, one trick is the double translation of the free text. For example, you can use Google service to translate a free text from Spanish to English, then back to Spanish. That translation service usually translates the sentence back using different synonyms, different words, or different sequence of words. And it usually adds diversity to the data set, right? And if we blend models using the double translating technique, for example, Spanish, English, Spanish, or Spanish, Portuguese, Spanish, if you build 2 models and then blend, probably you get higher accuracy if you are looking for it. Okay, a little bit of feature selection. So feature selection is a function of computer power and time available, right? There are classical algorithms, forward selection, backward elimination. The scikit-learn also have one function called recursive feature elimination. But the idea of forward selection is you keep adding one feature each time, and every time you add one feature, you train a model, cross-validate the results, and calculate the metric. And every time you add a new feature, you compare the performance of this new added feature with the performance without that feature, right? If the performance increase, keep that feature. If the performance decrease, remove that features. That's very single algorithm for feature selection. The same for backward elimination, but instead of you start with all the features and you drop one by one, and also comparing the metric without and with that feature, but dropping one by one, right? The problem of this approach is computer power. If you have a data set with 1,000 features, we need to run 1,000 times all the fit process, training a model 1,000 times, right? If your model take 1 hour to train, you have 1,000 hours to do that feature selection. It's a lot of time. So most of the problems, you don't have that amount of time available. So there are some tricks suboptimal to do any sort of feature selection that we use in Kaggle. For example, rely on the feature importance information calculated by the gradient boosting algorithm, right? In this example, I use the training fold to run a model just to calculate the feature importance. Then I set some threshold to select which features are really important, which features are going to drop from the data set. Then we run again the train fold with that new filter of the features, right? With the new set of features. Especially that kind of strategy, you can see it can improve very fast performance of your model, but at the same time, it's very easy to overfit also, because you are using information from the model performance to improve the own model, right? But that's why I say it's suboptimal. Feature importance on the gradient boosting decision tree, the calculation of feature importance is not so precise, it's not so accurate. So sometimes you may be missing some features that probably is better to keep in the model. But usually that kind of strategy works. Add some features that are nonsense or noise or useless in the model. For example, adding a random noise, one random noise to the model, right? One feature that is pure noise. There's no information aggregated on that feature, right? And then training a gradient boosting model or a linear model, doesn't matter. In linear, you can inspect the coefficients of each variable. In a gradient boosting, you will calculate the feature importance. But the fact is, if the random noise is, if there's some feature below the importance of the random noise, take a look at that feature. Probably that feature is not so important and deserves to be dropped for the model, right? This is another way to do pretty quick feature selection in a model. Leave one feature out. This is another technique, pretty interesting also, that saves a lot of time. It's based on you train a model, you already have that model trained. So when you are predicting the test set or the validation set, you remove one feature by one on that validation set, and for each feature, you calculate the metric again. But actually, you are not dropping. Actually, you are reaching 0 or reaching a value, a useless value to that feature. You are making that feature useless for the model, but you are not training the model again. You are using the model already pre-trained. You're just discarding the values of each feature, right? So you discard the values of the first feature, calculate the metric, discarding that feature, then the second, then the third, and so on to the last one, right? But how to remove the feature from a data set without removing, right? We just need to remove the values of the feature, not dropping that feature. We can hard write a fixed value to that feature, for example, 0. So we write 0 for entire column, and then predict the data set. Or we can just replace by the mean average of that feature, mean average value of that feature also, and predict. Or the one that works better, at least for me, is shuffling the results in order to keep the same distribution of the feature, so don't change the distribution, but add some kind of noise on that specific feature, right? Then what happens? Then you can compare the performance of the model, the full model with all the features, with the performance of each one of these dropped features, right? You just take the difference of the metrics. If you remove one feature and, for example, the accuracy drops a lot, means that feature is really important because model is depending a lot of that feature to have that accuracy, right? This is another way to do feature selection. Eventually, dropping one feature using that technique increases the accuracy of the model. So maybe something wrong with that feature, right? Maybe there's a lot of noise, or that feature is hurting the model. So this is another trick we're using in Kaggle. Adversarial validation is very important in Kaggle nowadays. What is the idea? The idea is try to detect difference in the distribution of features from the train set and the test set. It can happen in real life also, like variables that changes over time. It starts to hurt the model, right? Or what happens more in Kaggle is some values of some variables are presenting only on train set or on the test set, right? So doesn't make sense trying to predict something that is only on train or only on test, because the model, you never see it before. So the idea of adversarial validation is we concatenate the train and the test set together, but we assign a new target variable to that concatenate train and test. This new target variable you label as 0 for the train set, and we label as 1 for the test set. And we run a binary classification model. The idea of this classification model is to tell us which row is from train and which row is from test. If that model is able to tell us each row is from train or test, it means there's some issue with any variable in this data set, right? There's one variable or more in this data set that is telling to the model if the row is from train or from the test. It can be a variable that changes the distribution, a value that appears only on the train, or a variable that appears only on the test set, something that is not possible to train a machine learning model, right? So if the AUC of the adversarial validation is higher than 0.5, it's very likely that we have that kind of issue. So computing the importance of that adversarial model, we can see the top feature that is contributing with that differentiation between train and test. And very likely that top feature in terms of importance is the feature that have an issue. So it's the feature that you take a look at. Why the feature is doing that, right? And usually it happens in time series challenges when one of the features is time, right? Is the timestamp. Because the timestamp in train is different of the timestamps in test. So you train a model with the time, and the model can see all the timestamps in the train set, but when you predict in the test set, they have only new values that the model never seen before. So in that case, that new values adds noise to the prediction and decrease the accuracy of the model on the test set. So that's why that kind of feature needs to be fixed somehow. You can try to fix that feature somehow, but that kind of model is pretty interesting for Kaggle and can be used in real life as well. That's it. Thank you again.
Bueno, a continuación vamos a continuar con el turno de preguntas. No sé si alguien tiene algo que quiera preguntar.
Y antes de la pregunta, solo resumir brevemente lo que va a pasar ahora. Ahora vamos a hacer un breve turno de preguntas. Después vamos a hacer un quiz de 10 preguntitas muy rápido y el que gane se va a llevar un pequeño premio. Y lo siguiente va a ser ya las pizzas, ¿vale? Así que, ¿alguna preguntilla por aquí?
Hay que descargarse la aplicación Kahoot. ¿Kahoot en el móvil?
Ahí veo una pregunta.
¿Alguna pregunta?
Sí,
rápida?
ahí hay una. Te lo tira, ¿eh? Vamos a echarle un poco aquí de...
¿Esto funciona? Hi, Gilberto. Thanks a lot for the talks. I wanted to ask you, you hear me?
No.
Hello? Okay. I wanted to ask you, what are for you the main difference between Kaggle competitions and real-life problems? And which of these techniques that you have shown us can be easily translated to real-life problems? Thank you.
Okay, the main difference between Kaggle and the real-life problems is in Kaggle, the data set is already built, right? They give us a data set pre-built. Usually in real life, we need to build that data set, and to build that data set is necessary some kind of expertise, and a specialist to build that data set, or at least to review that data set. Also, in Kaggle, we already have the problem very well defined. So we just need to care about how to solve that problem. It's not the case in real life that we need to define the problem, acquire the data, label the data, prepare the data set to then start to solve the problem. Right? Also in Kaggle, the data set doesn't change. It's fixed on the beginning and it doesn't change for the entire 2 or 3 months of the competition. In real life, every day, data set changes. Every day is a new Kaggle competition.
Gilberto, I think we have time for only 1 or 2 more questions.
Por ahí abajo hay una.
Thanks. Are there a technique similar to cross-validation for time series problem? Or how do you deal when you have time series problem?
For time series, usually I use a walking forward strategy. I instead of splitting by folds, I split by periods of time that I walk forward every time validating a near feature of this data set. Do you know what I mean? I fix the train set and validate in a period of future. Then I walk forward 1 step or more step, validate in the feature. Then walk 1 more step and validate the feature. But the key is not just that. The key is to mimic the test set in Kaggle or the test set in real life problem. For example, in Kaggle, sometimes you are asked to predict 1 week in the future. So you need to do that kind of walking forward strategy in a 1 week periods, right? Then you concatenate all the predictions and calculate the overall metric over all these predictions. The problem time series is that you need to split in more than 5 folds. You need to split in more than 5 steps in that walking forward strategy. It takes more time to train, right? But it's better, especially if you need to tune hyperparameters, to use a larger period of time to do that. So maybe we will need multiple steps in the walking forward. Then don't calculate the metric for each step. Calculate the metric for the overall period of time, right? In order to make your model generalize better for the entire period and not just for the near feature. Okay?
Thanks.
Creo que tienes una pregunta al lado. Sí.
Y otra por aquí.
Hi, Gilberto. Well, thank you very much for this talk, first of all.
Hey.
And
You're welcome.
my question is, how would you tackle the problem that I'm about to postulate. We have a problem at work that it consists in predicting sales, right? We have a data set with a time series of an article, and we have for the target variable. The target is the sales, right? How many items is one article gonna sell tomorrow or next week, right? So, and we have negative values for the sales, and we know that some values represent pure sales, and other ones represent the difference between the sales and products that have been delivered back to the store. So we don't know if it's we don't really know for sure if a value is a real sale or the net, right? Net sales. How would you tackle that? How would you know how any kind of a statistical analysis or something to differentiate between which one is a
about
sale?
Experimentation, I believe. I will try different strategies and see which one works better in terms of the metric chosen for the problem. For probably mean absolute error or mean square error of the prices, right? But it's hard to say without looking at the data. But I will do everything that I said before. I will set a validation strategy based probably using a time series approach, using walking forward strategy. I will build the lag features for all the values present on the data set. Doesn't matter if it comes from sales or no, or pre-sales. But what matters in the end is the metric you choose, right? If you manage what to do, if you manage to find one way to decrease the error, keep that strategy.
Okay. Thank you.
The best I can say for you for now.
Thank you very much.
Una pregunta más por aquí.
Hello, Gilberto. Thank you for the conference. My question is, have you ever tried the software from your company to participate in a Kaggle competition? And if so, how did it perform?
You mean the AutoML from Apple?
Yes.
We never tried AutoML in a Kaggle competition. It's not the idea. The idea of our AutoML is to make the life for people easier. To everyone use AutoML, right? We never compare with any other tool, especially in Kaggle. Also, it's unfair to compare human inference with completely automatic inference.
Okay, so I think that we have a problem with the agenda, so I think this should be the last question. Thanks a lot, Gilberto.
Thank you. Thank you for the opportunity.
Muchas gracias. Y ahora el que se quiera animar, ponemos el
Ok, pues como hemos dicho varias veces hoy, tenéis que instalaros el Kahoot, K-A-H-O-O-T. Aquellos que no lo hagáis os vais a arrepentir dentro de 2 minutos, así que aproximadamente un 10% de la gente no sabe instalarse la aplicación, no sé por qué, es Google Play o en iOS, Kahoot, instalarlo. ¿Cuántas gente hay?
Ahí tenéis el código que hay que introducir en Kahoot. Van a ser 10 preguntas.
Hay gente a veces con móviles raros. Levantad la mano y nos acercamos. Hemos superado Sevilla, en Sevilla creo que eran 85.
Podéis hacerlo en equipo, ¿eh? 2 pueden hacerlo con un solo móvil.
Vamos a sortear un Google Home, ¿vale? Un Google Assistant, que no es muy fácil de repartir entre varios, pero si queréis, os podéis juntar varios en un mismo usuario.
Y lo más relevante, entrar en el hall de la fama de los que han ganado el Kahoot. Ok, ¿alguien queda? ¿Hace falta esperar a alguien?
99. A ver si llegamos a... Bien, hemos llegado a 100. Bueno, yo creo que ya vamos a dejar que Darwin haga la primera criba. Vamos a...
Sí, atentos, saldrán, sabéis que son 10 preguntas, sale primero la pregunta en la pantalla y hay 4 alternativas de respuesta que tenéis que pulsar en el móvil, ¿vale?
Vais a tener que elegir una alternativa de las 4 y el tiempo cuenta, ¿vale? O sea, si, por ejemplo, falláis la primera, podéis intentar ir a saco con las siguientes y recuperar posiciones.
Ok, ¿alguien que falte? Vale.
Ok.
Ok, empezamos, ¿eh? Ok. Alguien entra en último segundo. ¿Alguien que hace falta que le esperemos? Que levante la mano. Vale,
No,
vamos.
¿Cuántos hay? Es la pregunta. ¿Cuántos GrandMasters hay en Kaggle? Vale, 120 aproximadamente, ¿no? O sea que habéis acertado 34 personas. Como digo, los que vayáis por detrás podéis, con un fallo podéis ganar. Normalmente el que gana tiene algún fallo.
Vamos con la siguiente. Bueno, por ahora,
Bonito
ébola.
nickname.
¿Cuántas medallas de oro? Muy bien.
Muy bien.
Alberto va líder, seguido de Pollos Hermanas. Hijo.
¿Quién es el autor principal de este paper? No. De eso. ¿Quién es el autor principal de esa carta?
El autor de Keras, François Cholet.
Bien,
Pollos Hermanas.
¿Quién es? ¿Pollos? Si quiere salir del
Si quiere
anonimato.
develarse. Bueno.
¿No? ¿Quiere seguir en el anonimato?
Muy bien.
Vale.
¿Qué clasificador es un support vector machine con kernel lineal? Viendo la frontera de decisión. Muy bien. Greco en primera posición. Pollos Hermanas ha caído a la tercera. ¿Cuántos parámetros tiene la red neuronal?
Bueno.
Los pesos más los vallas.
Se lo ha acertado poquísima gente.
¿Cuál es el recall? Vamos por la séptima. ¿Qué es X en esta regla de 3? TensorFlow es a Google como PyTorch a Facebook. Greco sigue líder. Bueno, muy bien.
Quedan 2 preguntas nada más. Aquellos que vayáis por detrás, sabéis que tenéis que jugárosla y decir algo rápido.
¿Quién es el autor del paper? ¿Del libro?
Bueno.
Bueno, tenemos nuevo líder.
Queda empate técnico casi entre las 3 primeras posiciones.
Última pregunta. Complicada.
Bueno, 17
Era
personas solo han
complicado, ¿no?
acertado la última. A ver quién es el ganador. Tercer lugar.
Paula,
Bien,
segunda.
Y ganador o ganadora. Mitch. ¿Puedes levantar la mano, Mitch? Muy bien. Pues si puedes salir un momentito al escenario, si puedes venir un segundo, te hacemos la entrega de un flamante Google Assistant, un Google Home.
Tengo que añadir un dato porque cuando Gilberto
¿Qué trabaja en
preguntó,
Mitch?
Es complicado. Inversor, digamos, inversor.
Muy bien, enhorabuena, Mitch.
sé de buena oída que Mitch es Kaggle Master porque levantó la mano, ¿verdad? Cuando preguntó Gilberto. Miguel Pérez, hombre. Hemos hablado muchas veces.
Bueno. Enhorabuena, Mitch. Oye, pues tenéis unas pizzas y una cerveza esperando. Muchísimas gracias a todos por venir y espero que hayáis pasado bien.
Muchas gracias.